So our next speaker is Professor Abha Mishra from Industry of Science. She will talk on zinc oxide-based suspended carbon nanotubes thin film for development of thermally stable dynamic pressure sensing. Thank you.
Good evening, everyone. Thank you, Pradipto, for the introduction. So the work I'm going to present today is in collaboration with the LPSC ISRO. And we started it last year, and there is some progress we made towards the requirement. So the motivation of the work is carbon nanotube, using carbon nanotube, and I guess mostly everybody knows that what are the properties of carbon nanotubes. So just to give you a perspective of, we stand here with the CNTs and the most popular materials which we have been using in most of the applications is stainless steel, Kevlar, and so on. Of course, not the diamond. But where we stand with the properties, you can see here is the several orders of magnitude we are actually far ahead. So the idea when CNTs were developed, people really were very excited, and then there was a proposal that to build a road to space using carbon nanotube elevators. So far, still, I think it is still under progress. So, and another thing is, and that's because of the strength. Tensile strength is extraordinary, and the flexibility, you can actually get any shape, and most importantly, the carbon surfaces can be modified. So you can have the biological possible applications for, I'm not sure how successful we are in terms of these applications, but these are the projected applications in terms of drug delivery and so on, even for the growth of bone tissues. So these can be used as the substrate for it. So yeah. So one of the work what we did in the lab is in compression as well. So we compress these CNT bundles, which seem to be having, just a second. Oops. Just wanted to show you this video. So this sound is certainly not from this video. So what you see is the CNTs are getting compressed. This is a pillar of few micron sizes. And what you see is that these ripples start forming from the base. And that is the origin of energy absorption. So this compression is not really very useless thing, but certainly for microelectronic packaging, these can be used for the absorption of impact. And so in this case, certainly we don't have the recovery. So this actually pillar just remains as it is. So this is the mechanical response, and you can see that these are the ripples formed, and there is a large energy absorption in these pillars. So probably one of the reasons why we have this energy absorption is the graded functional properties. So which means that the density of CNTs when you make them, it varies along the length. So again, coming back to the space applications. So one of the projected application is moving from a huge Hubble design of the telescope to having something deployable, lightweight, and again, CNTs can be proposed to replace some of the current technologies. So in this direction, we had one STC proposal. So this is one of the properties which we can actually use CNTs to make these reflective membranes. It's a lowest CT and mechanical robustness and multifunctionality. And so this is what you see here in these graphs is we made CNTs reflective by coating aluminum, and then we showed that, okay, for the different wavelength, if you scan the wavelength, then the reflection also increases and reaches to around 60%. And here is the comparison of aluminum, but certainly some of the properties, it's because of the roughness, which we could not control, but eventually this experiment can lead to the reflective CNTs, as opposed to what CNTs are known for is having the 98% absorption of the wavelength. So in LPSC, there are working on fabrication of a lot of pressure sensors for absolute pressure sensing, propulsion systems, chamber pressure measurement for stage separation, aerodynamics characterization, health monitoring of satellite. So a lot of applications. And these are all MEMS-based sensors, and mainly aluminum or silicon-based sensors. So certainly there are some limitations which we highlighted and wanted to replace CNTs here as well. So one is the deformability because there is limitation, processing, and the thermal instability of these metallic structures. So what we did is I think I just skipped one slide. So CNTs have some electroactuation characteristics. So we apply field, they actuate. So what we did is we magnified that property by including zinc oxide. So zinc oxide has the piezoelectric characteristics. So we made this material, and then what we did is, so CNTs, you can actually have a large scale thin film. You can actually, so they have tendency to combine, and you can do anything. You can make pillar, you can make film, and what we did is we made a film, and then we transferred on top of this trench. So these are kind of suspended films. That's what we wanted for the pressure measurement. So this is the fabrication method where we had coating, we did transfer. So all these techniques we have developed in the lab so that we have this structure. And we use this structure not only just for the pressure, but there are a lot of other applications we have projected. So we did a quick simulation on this structure, if this is going to work or not. And what we found is there is a linear displacement with the pressure. So we were very optimistic to carry out this work further. And then we are here. So what we did is we did a quick packaging here. This is a lab packaging, which so this is this is the ohmic contact. So we don't have any issues with the contact, and this is the sensor, which we did in a very robust way, kind of. But let's see what is the response here. So we tested everything we built in the lab. So we didn't go to the market to get anything. And so this is the response. What we measured is what you see is the pressure: 1, 2, 3, 4, 5, 6. We could not go beyond it. So sensor seems like broken afterwards. But till 6 bar, we had quite very stable response, repeatable response. So that's kind of good thing to do. And then what we did is, this is the comparison. And we also measured the thermal stability. So we went from minus 10 degrees Celsius to room temperature, and response was quite stable. So we didn't find any drift there. One interesting thing what we have noticed, as we should be actually expecting also, to have a cell-powered response. So because of this electroactuation thing, we just noticed the reverse response here. We were able to get the pressure response without applying any electrical bias. So that we didn't explore it further, but that's kind of good to know. And here is the sensitivity when we compared, what exists in the market, and here we are. So we have pretty much enhanced sensitivity over a larger pressure. So that's a great thing. And the same thing what we have tested is making this in a commercialized packaging. And we tested the same thing. We did all the experiments again. And seems like we really had a good luck with that. So we could measure up to 2 bar, but we could not go beyond that. So that's another thing to do it further. We measured the TCR, pretty low TCR we could find with this film. And so that's pretty much. So here is the main person who has been working on this project, doing all the things, going to ISRO and conducting experiments there, Mr. Krishna Kumar, and PhD student who has fabricated all the devices, Mr. Vinod Panwar. And I got the financial support from ISC as IOE grant. Then we have IOE and ISC, and then DST, and I think there are several more grants also, especially STC grant. And now with this, I would like to thank you organizers for giving me opportunity to talk about this work. And thank you so much. So I'll take any questions if you have.
So we have time for a few questions.
So I saw your compression test where you were testing the compressive strength of your material. Did you test the helical strength at all? Did you try twisting, or no, only just linear strength?
It's uniaxial.
Okay. Yeah. Thank you.
Because you have used the CNT, Is there any plan to use the bio-inspired materials?
Not for me.
Okay.
So I'm not planning to do any, so I'm quite illiterate in bio stuff, so probably not.
Okay.
But yeah, certainly it can be proposed, and after we publish the work and all that.
Okay.
Yeah.
Okay. With that, let's thank the speaker.
Thank you.